Welcome back, guys. In this third lecture in our Theory of Partial Differential Equations course, I'm going to discuss some of the most important function spaces. So we already discussed what do you mean by Hilbert space and Banach space when we were discussing in our first lecture some of the most important things related to function analysis. And then in the very second lecture, we discuss some of the most important things in measure theory. And in today's lecture, we'll be discussing some function spaces, and obviously we'll be defining some norms over those spaces, and then we'll come to some sort of conclusion that, okay, whether these are normed spaces or Banach spaces, and so on. And after that, we'll be discussing one of the measure spaces when we are dealing with partial differential equations that we call LP spaces, and what are going to be the dual spaces of LP spaces. We have already defined what do you mean by dual space in our function analysis lecture. And at the very end, we'll discuss some of the most important inequalities that we frequently use when we study theory of partial differential equations. So let us begin with some sort of examples. So one example that I have is a space which is called the space of continuous functions, or omega. And how do I define it? It's a function which goes from omega to, let's say, R, and it can be R or Rn, depends. And f is a continuous function. So C0 means the space of continuous functions. The question is, can I define a norm on it? And the answer to that question is yes. So if I take a function from this space, how can I define the norm? So C0 norm over omega for this function is defined to be, take the value of the function for all points in the space, let's say omega, in the domain of the function, take its absolute value, and take the supremum for all points in omega. This is how we define the norm of a function in this C0 space. The question is this a norm? We can check all the properties of norm easily. And then the second question is it a normed space? So the answer is yes. And the next question will be, is it a Banach space? It means if I take, let's say, a sequence of spaces in this, what about their limit? Is the limit going to be part of the same space or not? So like, we'll not prove these results, but we'll state that, okay, what spaces among these are going to be Banach spaces, because this is really a crucial thing. Why it is a crucial thing? When we solve partial differential equations by using some sort of, let's say, Galerkin approximations, then we take a sequence. So sequence is some sort of approximate solution. How can you conclude there is a solution for the PDE? You have to find out the limit. So if the limit is in the same space, then you can say, okay, the solution belongs to this space and blah, blah. So we can discuss these things later on. So I have second example, that is X, which is CK omega. And X is just a name, so the space is CK omega. What is CK omega? So let me choose a different color. So it's a space of functions such that all the derivatives of f, all the derivatives of order alpha of f should be continuous, where the order of alpha is less than or equal to k. So here the function that I'm choosing is from Rn to R. It means it's a function where the arguments are n, x1, x2, up to xn. We can have two arguments, mostly we use x and y, and so on. And what is alpha? We call alpha to be a multi-index that is written in this way. It is some sort of vectorial notation. Alpha 1, alpha 2, up to alpha n. And d alpha means the derivatives of f, the alpha derivatives of f. It means that you have to differentiate your function f with respect to x1, alpha 1 times, which is going to be the first component of the multi-index alpha. Differentiate with respect to component 2, alpha 2 times, and so on up to differentiate with respect to xn, alpha n times. So there is like, what do you say, 1 correspondence. So you have alpha 1, so you differentiate alpha 1 times, alpha 2 times with respect to x2, alpha n differentiate with respect to xn, alpha n times. And how do I define the order? Means this thing that I mentioned so far. I'm going to define this to be the sum of these all alpha i's, where I runs from 1 to n. And obviously these alpha 1, alpha n should be what? They should be non-negative, because negative, how can you say that, okay, this is -1 derivative? Because in these spaces we are not going for negative derivatives, we are not going for fractional derivatives, and so on. So how do I define the norm of a function that belongs to this space ck omega? So what I do, I take all the derivatives of f of order alpha and take their sum over C0. C0 means I'll take their supremum, and I will sum these all the things for all alpha which are less than or equal to k. This is how we define the norm in this space. Again, the question arises, is it a norm? You have to check. So the answer is yes. Is it a normed space? Yes. Is it a Banach space? We have to check. Okay. So the next example that I'm going to put is what we call holder spaces. Because these things are also really important when we are discussing partial differential equations. So one example that I have is C0 omega over omega. So one is small omega, another is capital omega, where the small omega belongs to 0 to 1. And how do I define this space? I define this space in this way. C0 omega over omega is defined to be all the functions from omega to r such that the difference between the values of the functions is bounded by some constant times difference between the arguments raised to gamma for all xy in the domain. So like I define this space to be all the functions that satisfy this property for different gammas. Then I have this space C0, 1. So I can replace gamma by any number between 0 and 1. So C0, 0 and C0, 1 and C0 half and so on. Mostly you use the numbers between 0 and 1. Mostly excluding 0 and 1. But 1 is also important thing, because if you put 1, then this space is called what we call the space of Lipschitz functions. Okay, so this is the space. So on this space, I'm going to define a norm, but before defining a norm, I'm going to define what do I call holder subnorm. And what is holder subnorm? It's like I give you a function u. Why I'm using notation u? Better to use f. I give you a function f, and this notation is like what we call the subnorm notation of C0 gamma is take the difference f of y minus f of x, their absolute value, divided by x minus y to the gamma and take their supremum for all x, y in gamma. And you have to be careful that x should not be equal to y, because if x is equal to y, then this is going to be undefined. And this is how I define Holder subnorm. Then how do I define the norm of a function in this space? So this is the norm over C0 gamma of a function is defined to be, take the function, take its C0 gamma norm, sorry, C0 norm, it's a usual C0 means usual supremum norm, and add to it the Holder subnorm C0 gamma. So how do I define this norm? So I define this norm by the sum of this C0 norm and sum of this Holder subnorm. So this is how I define this norm by taking these two sums. The question is it a norm? So again, the answer comes from, you have to check that, okay, whether all the properties of the norms of the norm are going to be satisfied or not. Okay, let us move ahead. In general, what we can say, so in general, what can I say, that Ck omega, first I define the space C0 omega, now I'm defining the space Ck omega, is all the functions such that their alpha derivatives are C0 gamma, such that this alpha is less than or equal to k. So what I say that, give me a function which is C0. Now differentiate the function for all alpha and check that whether those all the derivatives are also in C0 gamma. If this happens, we say that, okay, this is going to be the space, this is going to be the space Ck omega. So this is how we define this space. And we can also define Holder subnorm over this, and we can also define the norm over this space, because we need Holder subnorm to define a norm on this space. Otherwise, the things will not make sense. So how do I define Holder subnorm? So Holder subnorm, and how do I define it? So U, Holder subnorm Ck omega, where omega is defined to be, take all the derivatives of f evaluated y minus all the derivatives evaluated at x, divided by x minus y to the gamma, and there should be absolute value. Take their supremum for all x, y, and omega, where x should not be equal to y, and sum them for all alpha, which should be bounded by k, because this is the space Ck omega. And how do I define this Ck omega norm over this? Is take the norm of u. So one thing is that I have like replaced u with f and f with u. So let me make the things consistent. I think this should be f, this should be f, and this should be f. So take the Ck omega norm. This is simply the supremum norm that we have already defined. Plus, so add Holder subnorm to it. So this is how you define the norm, and you have to check that, okay, whether this is a norm or not. And then the second question is the space going to be a normed space? Obviously, if you have a norm and it is a norm, it means it satisfies the properties, then it's going to be a normed space. And I'm going to provide a fact, and the fact is that the space C0 omega, the space Ck omega, the space C0 gamma over omega, the space Ck gamma over omega, all are Banach spaces. These all are Banach spaces. Like, you have to check that how these are Banach spaces, and You have to check, you have to take a sequence, and you have to just take the limit and see that, okay, whether the limit belongs to the space or not. So this is a fun stuff, but the problem is this is not what we are supposed to do. We have to go ahead and discuss partial differential equations. So LP spaces, the next thing is LP spaces, where this P should be between 1 and infinity. So before moving ahead, I'm defining some curly LP spaces. So curly LP over some domain E is the space of all the functions from E to R such that if I take the power P and integrate over this set E, the Lebesgue integral should be finite. This is when P is between 1 and not infinity. So P is between 1 and infinity, but excluding infinity. What happens if P is infinity? Then my curly LP or calligraphic LP is a space of functions from E to R such that the essential soup, the essential supremum of F should be bounded on the set E. So this is how I define the calligraphic LP space and or the curly LP space for these two different cases of P. And for this first case, this is like P integrable space, P integrable functions. It means, okay, like you take the pth power and take its integral, it should be finite. And for the infinity case, you take the essential supremum. So what is the difference between the essential supremum and the supremum of a function? So let me define essential soup first. Essential soup of a function over some set E is take all the numbers k which are non-negative such that the function is bounded by k almost everywhere, and take the infimum of this set. And what do I mean by this? I can give one example that if I have, let's say, if I have a function, let's say like this, and I have another function, let's say like this. So you can see simply that, okay, what should I do? I should make it so if I take the supremum of the function, let's say this is the supremum and this function goes down from here, let's say it goes down here, it goes down from here, goes down from here. So this is going to be the supremum of this function. This is supremum and this is supremum in this case. But what is going to be the essential supremum of this this function? This function, this is going to be the essential soup. But for this function, since this point has what we say measure 0, so we'll not include that point. So the essential supremum is going to be somewhere here. So in this case, the supremum and essential supremum are different. You can see this is the supremum, but here somewhere here is going to be the essential supremum. But in this case, the essential supremum and supremum are going to be same. So in the case of essential supremum, you are not going to include the points that have measure 0. So you are just going to exclude those points, not include those. So this is going to be the difference between supremum and essential supremum. And one more observation is that whenever f is equal to g almost everywhere, so I can say that, okay, this is my function f, this is my function g. So these two functions are equal almost everywhere. The points where these functions are not equal, they have measure 0, because there's only this point where these two functions, let's say, have a different value. So I say that, okay, these functions are equal almost everywhere. In this case, if I integrate f over some measure, should be equal to integral of g over mu, because in integration you cannot include those exact points. Like you integrate over up to this one, this area, and you integrate over here, so there is no any contribution from this point, and simply you integrate this function and you get the same result. So this is implication like this: if f is equal to g almost everywhere, then integral of f with respect to that Lebesgue measure or whatever the measure is same as integral of g. So like now we have like a class of functions whose integrals are same. I can take different functions, but their integrals are going to be same. Then I said, okay, these functions are equal almost everywhere. So what is calligraphic LP space or curly LP space? It's the space of functions. But the LP space that I'm looking at, that we are interested in, is the space of classes of functions, where if I take a class F, they all can be different functions in the essence, but they are equal almost everywhere, and hence their integrals are equal to each other. So this is the idea. So we define these spaces by, so LP over E is curly LP over E, and reduced our quotient by this what we call relation, what integral operation. So where P is between 1 to infinity, these type of spaces are called quotient spaces. But you have to just keep one thing in your mind, that okay, this space involves some sort of functions, and this space involves classes of functions. So what does this involve? So f belongs to LP implies f is class of functions. The class of functions, so whatever function you take from that class, their integrals must be equal, and their integrals must satisfy this property. So it's a class of functions. So this is the minor difference between these two things. So here we define what do you mean by LP spaces, where P is between 1 and infinity. We have a different case when P is equal to infinity. So the next idea is, or the next thing that we are going to discuss is the dual spaces of LP. So the dual spaces of LP. So the dual space of LP is denoted by LP star. And what is this? This is the space of all the functionals on LP. It means this space contains functions that take value from LP and give you something in the set of real numbers. So one example that I need to quote here is, let me define an operator TG which takes me from LP and sends me to R. And how do I define that operator? TG, when operated on some f, is defined to be integral of f times g times d mu. So like I have taken a function g, and with respect to that function g, I'm going to define a class of functionals that take a function f from LP and give me something, because you know very well this integral is always a real number, so that take me towards a real number. What can I say here? That okay, this f belongs to LP, and Okay, this belongs to LP and G belongs to LP prime, where these P and P prime are conjugate numbers. It means that 1 over P plus 1 over P prime should be equal to 1. How can I say this? I'm using here Holder's inequality, and we'll be discussing what do you mean by Holder's inequality in the maybe in the end of the lecture. Okay. So like if I take a function from LP, then I can take a function from LP prime, and with the help of that function, I can define a functional that takes me to the set of real numbers. So like for each functional that belongs to LP star, there is a function in LP prime that can behave in the same way as we need. And how can I find out the norm of this operator TG? You know very well, whenever we have an operator, whenever we have a functional, how do we define norm of it? So I operate TG on F and take its norm. So I will use this absolute value because this is just a real number, and take the norm of F over LP, and I take their supremum for all F which are not equal to 0, and F should be in LP. And by using Holder's inequality here, so I'm using Holder's, and we'll be quoting this result very soon. So Holder's inequality, which shows that, okay, this is less than or equal to, since this TG of F is defined in this way, we have this thing here. So I define TG of F in this way. So I can apply Holder's inequality here, and I can write this is less than or equal to LP norm of F and LP prime norm of G divided by LP norm of F, and I can cancel out these things. Then I have this thing is LP prime norm of G. So this operator norm is bounded by the LP prime norm of the function G, which belongs to the space LP prime. So what can I say here, that if I take any operator in the space of functionals of LP, then I have some sort of 1-1 correspondence. It means it for each operator, for each functional in LP star, I can find a function in LP prime such that there exists some sort of correspondence between those. So then I can maybe quote a result or a remark or what you call a theorem that says that there exists a mapping from LP prime to LP star. LP prime is a space like LP, and LP star is the space of functionals, or it's a dual space where what is P? P is between 1 and infinity, excluding infinity. And whenever I operate J on some function G, it gives me some sort of functional TG. So then we say that this mapping J is onto, it means that the set of range is basically the Codeman set. And if I take the norm of J of G, it's same as the norm of TG. So using this theorem, we can say many things. One thing is that, okay, the dual space LP star can be understood as the space LP prime. So there is like a correspondence between these spaces. So this gives us some sort of hint that how do you define the dual space of LP space, and how do I define it? So it's just the functional, but how do I find the space of dual spaces? So maybe I can make a short table for you that might be helpful. So I'm going to make a table like this. Sorry. Okay. So I have a space LP when P is between 1 and infinity. The second case is I have a space L1, and the third case is I have a space L infinity. So these are different cases that we are going to discuss. And my question is, what is going to be the dual space of these spaces? The dual space is denoted by LP star. So the dual space of LP is LP prime, where P and P prime are conjugate numbers, and the dual space of L1 is L infinity. And the problem is, what is going to be the dual space of L infinity? It's not L1, it's some sort of space which is bigger than L1. So we'll not go into this discussion. This is going to be a more rigorous version of the discussion that you can see when you are doing a course on function analysis. So this is bigger than L1. And there are two other things that I want to share with you. Maybe we are not going to discuss, but whether these spaces are separable or not. So we have already discussed what do you mean by separable spaces. LP is separable, L1 is separable, but L infinity is not a separable space. The separable space means like you can find a countable dense subset for the space, which is maybe an extra discussion that we are not going to do. And the third thing that I want to discuss is either these are reflexive spaces. So LP is a reflexive space. Reflexive space, in simple words, it's not the definition, it's not the theorem, it's just my idea that, okay, can you find the double dual? So you take the dual of LP, you get L prime, LP prime. You get the dual of LP prime, you get LP back. So you can go. So the dual of L1, the dual of L1 is L infinity. And what is the dual of L infinity? I don't know. So this is not reflexive. And this is not either. You can understand why. So like, can you find the double dual? Like what is the dual of L1? L infinity. What is the dual space of L infinity? I don't know. So it's not reflexive. So this is how we define, okay, which space, what are going to be the dual spaces, and whether these are separable or reflexive spaces. So the next thing is that I'm going to discuss some inequalities, which are really crucial inequalities, and these will be the part of homework that I'll be giving you. And if you do the homework, that's going to be a good thing. And if you are done with that, you can tell me in the comments, and then I will tell you, okay, what is the way to share homework with me. Then I can check it and I can give it back to you. So it depends if you are interested. So what's the Holder's inequality? I'm taking L from LP, and I'm taking G from LP prime, where I know very well 1 over P plus 1 over P prime is equal to 1. Then what is the conclusion? F times G should be in L1. This is the one conclusion. So F is an LP and G is an LP prime. Then F times G should be in L1. And this thing can be checked easily, can be proved easily. This is maybe present in many standard books on function analysis. And one thing else that this is one conclusion, and the second conclusion is the L1 norm of f times g is bounded by LP norm of f times LP prime norm of g. So obviously these norms are over set E. So these are two conclusions for Holder's inequality, and this is really a crucial inequality, which we'll be using time and again. So the second inequality is what we call Young's inequality. And how do we define it? Let me take two real numbers, a, b. Then what happens? A times b, so their product is always less than or equal to a to the p over p plus b to the p prime over p prime, where 1 over p plus 1 over p prime should be equal to 1. This is main conclusion of Young's inequality, which we'll be using again and again. And you can also prove this inequality. And third most important inequality that I'm going to quote is called Minkowski's inequality. Minkowski's inequality. And how do we define it? It says that, okay, whenever p is between 1 and infinity, including infinity, then I have the LP norm of f plus g is always bounded by LP norm of f plus LP norm of g. This is like what you say, some sort of advanced version of triangle inequality. And Young Holder's inequality is what we say Cauchy-Schwarz inequality. So Cauchy-Schwarz is going to be the reduction of Holder's, and triangle inequality is a reduction of Minkowski's inequality. So after this, I'm going to define what do you mean by convolution, and then I'm going to propose a result related to convolution, and then we are going ahead for maybe a couple of more things before ending this lecture and moving ahead. Okay, so I'm defining convolution. So I'm saying, okay, recall that u convolved with v evaluated some x. So I have two functions, u and v. Their convolution is defined to be evaluate u at x minus y, evaluate v at y, and integrate them over Rn. Over Rn or R depends upon if your function is from R1, R2 up to Rn. So this is how I define the convolution of two functions. Then I have a proposition. So there are two parts of proposition, and they say that let uv are from L1, then u convolved with v is also in L1 of Rn. So if I take two functions from L1, then their convolution is also L1, and u convolved with v, their L1 norm over Rn is always bounded by L1 norm of u over Rn times L1 norm of v over Rn. So this is one of the most important inequality, which involves convolutions. And when we find the solution of heat equation or Poisson equation by using their fundamental solution in convolutions, we always include these inequalities to find some sort of norms or the bounds on the solutions of heat equation or Poisson equation or Laplace equation. So the second thing that I have is, now I'm going to provide a general version. So I'm taking U in L1. Let U is in L1, but I'm taking V from not L1, but LP in general. So one is from L1 and another function is from LP. It implies what? That the LP norm of U convolved with V is bounded by L1 norm of U and LP norm of V. So this is like a general version, and we can also prove one result from the other result easily. There's going to be no difficulty in proving these all the results. So after this, maybe I define one last idea, and this idea is really crucial when we are dealing with partial differential equations, and we'll come to know that, okay, why these results are so much important. So I take a function phi, which is C infinity. It means I can differentiate this function infinite times, and all the derivatives are continuous. The space of smooth functions with this little c denotes the compact support. It means these functions are non-zero on a compact set, and beyond that, these functions are zero over Rn. And if I integrate this phi over whole Rn, my result is 1. And I'm going to say that, okay, the support of these functions is on the ball, or this function is on the ball. Its center 0 and radius 1. What do I mean by that? Sorry. So I can, I'm not going to include this. So this is 0. Sorry. This is 0. This is 1. This is 1. So my function will look like this. So you can see beyond 1, my function is 0 on both sides. It's 0 here, it's 0 here, and it's non-zero over this ball. And if I integrate this function, this should give me exactly the answer 1. So what can I say? Now I can define a sequence of functions, what we call phi epsilon of x. And what am I doing? I'm taking the same function phi that I defined earlier, which is smooth function, C infinity, compact support, and its integral is 1. So I'm going to scale x by x over epsilon and divide this by 1 over epsilon to the n. And now I can say one thing, that these all phi epsilon are in L1, because you can integrate these and their integral, the L1 integral should be finite. And the second result that I can quote is, if I integrate these all the phi epsilon over whole Rn, the result should be equal to 1. You can simply check these things by some sort of transformations. Okay, so how do these functions look like? So let me just tell you, okay, this is 1, -1, and 1. So this should be -1 as well. This is 0, and my function, one thing is that, let me take this a bit down so that I can show you exactly what do I mean. So this is like this. So if I'm taking epsilon to be smaller and smaller number, then my functions will look like this. Then my functions will look like the functions are going to be, this function is like this. Then these functions are going to be squeezed in from here, and from the center, they are going to be increased. So like you will get finally a delta function if you know the delta function. So this is the sequence of functions phi epsilon, and let me now take it back where this should look good. Now it's better. Okay. So these are like a sequence of functions, and let's say the support of this one is from epsilon to negative epsilon. So the support is ball at center 0 with radius epsilon, support of these functions. Then I call this phi epsilon, it's a sequence of functions because I can change epsilon, is called a sequence of Mollifiers. So this is the important thing. It's called a sequence of Mollifiers. And one last result that I'm going to quote is that this phi epsilon evaluated at x goes to 0 as epsilon goes to 0 almost everywhere. Like if I'm going to make epsilon smaller and smaller, these are going to be squeezed in, and there is going to be a one point where the value of the function is infinity, and at rest of the points, the value of the function is going to be 0. But at one point, the value of the function is infinity, but the measure of the one point is 0. Then we say that, okay, this function is 0 almost everywhere. We know very well how do we define almost everywhere thing. So this was a sequence of Mollifiers, and these Mollifiers are really crucial when we are doing the theory of partial differential equations. So let me recall what we did. We started from some function spaces, the spaces of continuous functions and k times differentiable functions, Holder spaces, and LP spaces are really crucial. The dual spaces of LP spaces that we discussed. And we also discussed a table about dual spaces, the spaces which are separable and which are not, the spaces which are reflexive and which are not. And Holder inequality, Young's inequality, Minkowski's inequality. Then we provided some results about convolution, some inequalities, and finally we defined what we call the sequence of Mollifiers. So this I think ends the lecture over here, and in the next lecture, I think we'll discuss weak derivatives and the related stuff. And maybe after next lecture, I'll be posting the homework, and I'll be putting the link down in the description for the notes as well as the homework, maybe in the next lecture. But for this lecture, I'll be posting the link in the description for the lecture notes. And then after weak derivatives, we can define maybe Sobolev spaces in the same lecture, and we can go ahead with the advanced stuff. Like we have to define Fourier transform, then we can go to more advanced stuff. So see you by then. See you in the next lecture.